Now we come to D9, Newton's law of universal gravitation. So Isaac Newton, in the year, 1687, when you have the publication of the Principia, then we find that we have the universal law of gravitation. Now, I'm going to see if I can figure out how we might arrive at this using some historical recollection of someone that knew Newton. And Newton was at the University of Cambridge in 1665, and there was a plague, a great plague. He had to stay at home because of the plague. Schools canceled, and here Newton had this idea that of the universal gravity, that the apple that falls to the earth is the same force that keeps the moon in its orbit around the earth. And about 50 years later or so, Newton was talking to Stukeley about the falling apple, and Stukeley reports, I paid a visit to Sir Isaac in his lodging in Kensington, and he dined with them. And after dinner, the weather was warm. They went into the garden, drank tea under the shade of some apple trees, and only he and Stukeley were there. And amidst other discourses they were talking about, he told me he was in the same situation when he formerly had the notion of gravitation coming to his mind. Why should that apple always descend perpendicular to the ground? Thought he was thinking to himself, occasioned by that apple falling. And he was in a very contemplative mood. And why would it come down? Why not go sideways or upwards? But constantly falls to the Earth's center. The Earth draws it. There must be some drawing power in matter. In other words, matter must be attracting matter. And the sum of all the drawing power in the earth, so if you were to look at every point of matter on the earth acting on the apple, they seem to all sum up to falling to the center. And Newton's invention of integral calculus there actually does the integral to sum up all the forces using his law, and indeed you can show that it's toward the center. So if we look at statement 1, we will say that there must be a drawing power in matter. And matter draws itself, to other matter, in other words. And the sum of all those is toward the Earth's center. So then 2 here, if the matter draws matter, then Newton reasons it must be proportional to matter and its quantity. All right, so in other words, we're saying here, if matter draws matter, it must be proportional to its quantity. All right, so some kind of proportionality. Proportional. So that means the law of gravity, F, would be proportional to the masses. So there's 2 masses here. We'll say the mass of the earth and the mass of the apple. So that would mean the force is proportional to big M and proportional to little m. So we would then say here mathematically, say some force is equal to some constant times big M and then little m and then some function of the distance between the apple and the center of the earth. Or if you think of 2 points, this distance r would be relevant. And you get farther and farther away, say from each other, then the force is going to get smaller and smaller. So what gives the dependence then of r? And that's a tough problem, and one of the most important ones in the history of physics, the history of science. And I'm going to see if we can arrive at some reasoning here. So what we're going to do is consider the apple first. All right. So this is not exactly, the reasoning, because the one problem that they were trying to solve is the law of Kepler's third law. But I want to show you a way to arrive at this f of r by considering the apple, acceleration of the apple, and the acceleration of the moon. So the acceleration of the apple, we already know. It's 9.8 meters per second squared. All matter has that acceleration. So what about the moon? Well, for the moon, the acceleration for the moon, okay, this is that moon. Say this is apple, and now moon. The acceleration of the moon would be here, the magnitude would be the velocity of the moon squared over the radius of the orbit. So this is the speed of the moon around the earth, and this is the radius of the orbit, which should be from the center of the earth out into the moon. So this would be your r in this case. All right, so here, let's see if we can figure this out. Well, the velocity of an object that's in some circular path would be the circumference 2 pi r, and then divide by the time it takes to make one path. That's the formula. Now this distance is 384,000 kilometers. That's the distance from the center of the earth to the center of the moon, which would be the orbit. So what is the lunar velocity? Well, then the time it takes to go around the earth is 27.3 days. So we're going to have to use that down in here and get it into seconds, and then put this in meters up in here. So in the book, I worked this out, and you get, for the acceleration of the moon, you get 0.0027. So now what we're going to do is compare the acceleration of the moon to the acceleration of the apple. And see, the moon has a less acceleration, it's far away. The acceleration is not as strong, see, as great as the apple. So you would have 0.0027 meters per second over 9.8. And this is pretty close to 1 over 3,600. But now, if we look at the radius of the moon orbit, and compare that to the radius of the Earth, since that's where the apple is. The apple's at the Earth's surface. You get 384,000 kilometers over 6400 kilometers, and that is about 60. Now look at this. You take 60 times 60, you get 3,600. And you do the inverse, and you can see that we square and do the inverse, we're onto something. So this suggests that by moving from this close value to far away, your acceleration is 1/3600, and the ratio of the radii are 60, so it suggests a 1/r squared law, where now I'm using little r to represent any of the r's. So that would mean that the force is big G, big M, little m over r squared. This would be the law of universal gravitation, and it would apply to the Earth and the Moon. And this is giving the magnitude. If we were to draw a picture of the force law here, where you have, say, some big M and some little m, like this, and that distance between the two is your r, then the force would be toward each other, equal and opposite toward each other. Force here and force there, given by this equation. And that's such an incredible achievement to come up with this law that Isaac Newton did.